Hello, Earth Science students. Today we're going to be talking about the life cycle of stars. And so we're going to be talking about the birth of stars, what actually makes a star, what happens in the inside of the star that produces so much energy, and then what happens as a star dies. And what we'll find is that stars have different fates depending on the mass. And so we're going to make a big flow chart that has all the details of every little aspect of a star's life cycle. So it'll be kind of like uh, a one and done, all the information that you really need to know about the star's life, including some stuff about nuclear fusion and nucleosynthesis, which is the creation of new elements. We're talking about elements on the periodic table. These guys, where these elements actually come from, all that stuff will be shown in this flow chart. Now, we're using just a blank piece of printer paper for this, and I just want to show you what it's going to look like when you're completely done. This is a finished product from last year. A lot of information. We're really filling out this entire thing. And so there's going to be sections we're going to be writing pretty small. So I'll do a series of we'll zoom in so we can see what we're drawing, and then I'll zoom out so you can kind of get a sense of how much of the page I've used. And then you can gauge whether you're using too much space or too little space. And now the thing is remember, this is a flow chart. Again, I'm going to show you the finished product has a series of arrows. It's kind of going around this way. If you're finding that you're kind of running out of space, as long as you're indicating an arrow and it's going onto the backside, I'm okay with that as long as you can follow the track or the pathway of the star life cycle. So I would recommend using pencil for this in case you make mistakes. I'm a little bit more bold, so I'm using pens. Just so I think the pens will show up a little bit better under the document projector. But we're going to start off in the very top left-hand side and kind of see my finger for scale. And what I want to do, this is the beginning of stars. This is star birth over here. And so I'm just going to draw. It starts off as dust and gas. So I'm going to draw kind of this little cloud of dust and gas. And I'm just going to put some specks in there to represent that dust and gas. There's different particles in there. I'm just using some different colors here, like blue and red and black. So dust and gas particles. What we find is typically the dust and gas clouds that are the places what we would call stellar nurseries, where stars are born. I'll just label this first, dust and gas. So these places, these dust and gas clouds, typically we find in space are about 92% hydrogen and about 7% helium. 92% hydrogen, 7% helium. You're like, wait a minute, 92 plus 7, that doesn't add up to 100%. So there may be some slightly heavier elements thrown in there, but they're less prevalent. Mostly we're going to find hydrogen and helium in these gas clouds. Now, if we have particles of dust and gas, remember those things, even if they're the tiniest little specks of dust and gas, they're going to have mass. And if they're close together, we've got mass, we've got distance. Those are the things that are necessary for things to have a gravitational attraction. So there's going to be a force of gravity between this little speck over here and the one over here, gravity. So because there's gravitational attraction between all these dust and gas particles, they're going to start being attracted to each other. They're going to start pulling together under the force of gravity. So I want you guys to draw, let's see, can we see this? Draw an arrow going to the right. And we're going to label that arrow gravity, just to show us that what's going to be happening in this next step is a result of gravitational attraction. So as gravity is pulling all of these molecules together, what's going to happen is they're going to start bouncing off of each other, crashing into each other. And what tends to happen is the temperature starts going up. It'd kind of be like if you guys were imagine that all of you are little dust and gas particles and you guys start getting closer and closer together. Let's say I threw you all into a closet together. You'd be bumping into each other and stuff. And the temperature inside that closet that you're all shoved in is going to go up. It's going to get super hot in there. Now, what happens is if we got enough dust and gas particles that are squeezing together and the temperature gets high enough, what happens is it starts glowing. We talked about how something has a lot of energy. one of the ways it can show that energy or give off that energy that it has is by giving off light and heat. So this mass gets hot enough to where it starts glowing red. So I'm just going to use some red right here. See if I can zoom in a little bit. We can see this a little bit easier. And I'm going to draw just a little, it kind of looks like a star, but we're going to talk about this isn't a star just yet. What we call this is a protostar. Protostar. So what that means is it's not yet a star. We're going to talk about what actually makes a star, but this is at least a mass that's hot enough so the temperature has increased. That's an up arrow. Temperature has gone up, and it is now hot enough to emit red wavelengths. This symbol right here, this is the Greek symbol lambda. That's just the shorthand for wavelength. So we're now hot enough that we're going to start emitting red wavelengths. Remember, in terms of the visible light spectrum, red is the longest wavelength. It's the lowest energy compared to red, orange, yellow, green, blue, purple, indigo, and especially violet. So it's just hot enough that now it's starting to glow. I'm just doing a different color here to make this stand out a little bit. This is an important note. So I said this isn't a true star yet. So I'm just writing not a true star. And the reason why is because something that categorizes a star is that there is something called nuclear fusion happening in its core. Nuclear fusion, we're going to get into that, but that is a requirement for a star to be a star. Right now, this thing is hot. It's producing light. It's glowing red, but there's no nuclear fusion yet. So we call it a protostar. But here's the thing, as this is contracting under the forces of gravity and things are being pulled into it, the temperature is going to continue to go up as further gravitational attraction happens. So we're going to draw another arrow going to the right here. And I'm going to say further contraction. So that means coming together. Further contraction from capital G, we'll just use for shorthand, that's gravity. We get further contraction from gravity as more and more things are getting pulled. This mass keeps going up and up and up. And what happens is as it's further contracting, the temperature is going to continue to rise. So under here, just underneath this arrow in blue, just to make it stand out, remember the temperature goes up even more. And now hydrogen, which is what we started with, mostly hydrogen, finally fuses. Again, if you're like, wait, what do you mean by nuclear fusion? What is it when hydrogen is fusing? What does that mean? We're going to get into that. But in short, it's basically we have the nucleus of atoms. In this case, it'd be the nucleus of hydrogen is coming together with another nucleus of hydrogen, and that starts making heavier elements like helium. It's basically like taking two atoms together, and what you get is one larger atom from that. Now, what I want to do, we've drawn an arrow going here. I want to draw what this actual star looks like. So at this point, if we have fusion happening, now we actually have something we can consider to be a true star. And this is the way that we can kind of depict this star. Let's see. So I'm kind of over to the right a little bit. I want to draw a circle with a core on the inside. So it kind of looks like a donut right now. And we call a star that is kind of living its life, just doing, there's nuclear fusion happening in the core of the star, in the middle of this donut. Hydrogen is fusing into the heavier element helium. And this is kind of just the engine that's driving the star. And it's just kind of, that's the way a star lives. We call this main sequence. So right above, we're just going to title this main sequence. Main sequence. So that's a star just kind of normally living its life. Like that would be, if you guys were stars, you guys would be in the main sequence. You guys have been born. I would say you're kind of, you're almost at the point where you're done growing. You're kind of just, at this point, you're kind of just living your life. That's what this star is doing. Now, here's the thing. is if there's nuclear fusion happening in the core, that heat and energy is being released. This process of hydrogen fusing releases a lot of energy, and that energy pushes outward. So I'm going to draw arrows pushing outward from the core of this star. So that's the outward push of heat energy from the engine that's driving this star. Now, if we've drawn arrows like this, we would imagine the star would just get bigger and bigger because of this outward force. But you got to remember, this thing is now it's pretty massive because enough dust and gases come together to actually make this thing pretty sizable. So it has a pretty good amount of gravity. And we know that gravity is pushing inward. And so these arrows are kind of counteracting each other. And it's a nice balance. So the outward energy that's coming from the fusion in the core is balanced with the inward pull of gravity, and it's nice and balanced. We actually have a word for this. This is called hydrostatic equilibrium. Hydrostatic equilibrium. You're like, man, that sounds like a really big word. Do we have to know that? This is not going to be a vocabulary term, but it is useful to kind of break it down to get an understanding of what it's actually referring to. Hydro sounds like water. Static means it's not changing. Equilibrium is also, we can kind of get a sense of a balance. If something's in equilibrium, it's in balance. So this is just referring to hydro is like, this is like gases that are moving around and stuff in the plasma that stars are made of. It's moving around like a fluid. That's kind of the hydro portion. Static means it's not moving in the sense that this star is not growing or shrinking. And equilibrium is this outward balance with the inward arrows. So in parentheses underneath this, I just want to kind of put that into some words. We have the balance of outward thermal pressure from fusion. So remember that those outward arrows are coming from this fusion process that is the engine in the core from fusion. And the inward force of gravity. So, hydrostatic equilibrium, balance of outward thermal pressure from fusion and inward force of gravity. Now, I want to add a little note underneath here, making it a different color just to make it stand out. Most of a star's life is spent in this main sequence. So this, we would quantify it as about 90% of the lifetime of a star is spent in this main sequence phase where it's in a nice balance, energy going out, balanced by the inward force of gravity. So at this point, I'm just going to zoom out so you can see how much of my printer paper I've actually used. There's still plenty of space. If you're like, oh my gosh, I've used up like half of my page, I would maybe start writing a little bit smaller. But remember, as long as you can follow your arrows, you can go onto the backside as long as you can follow. It's perfectly fine with me. Now, what I want to do, I keep mentioning that there's nuclear fusion of hydrogen happening in the core. What does that actually look like at the atomic level? So in this part of our flow chart, I actually want to kind of zoom in on what's happening for nuclear fusion. So I'm going to write this vertically. Zoom in with a little bracket showing that we're zooming in. We're kind of pretending we're going all the way down. Like this is really, really big. We're going all the way down to the atom sizes. And I want to take a look specifically at hydrogen fusion in the core. Hydrogen fusion in the core. So we're looking in the center of our donut here. Now, what I'm going to draw is a very simplified version of nuclear fusion. It is a little bit more complex than this, but I think this will just give you the gist of what's happening. So let's say that we have hydrogen in our core. I'm actually going to draw 4 hydrogens. I'm drawing them pretty small. I'm putting little H's in there for hydrogen. You can see there's hydrogens there. And remember, there's gravity and it's pushing it inwards. We're imagining all of these under the force of gravity are being pushed together. That star is really heavy, so it's pushing all that hydrogen together. And it's enough energy that we're actually going to start fusing the nucleus together. Nuclei, plural. This fusion process is going to result in a larger nucleus, helium. Might be kind of hard to see. That's He, helium. So we started off with hydrogen. This is our periodic table. We got 4 of those hydrogen nuclei together, and now we've made helium. Now, one thing that I want to add some numbers to this because there's something important that's happening here. Let's say we had, hypothetically speaking, 100 grams of hydrogen coming together and fusing. What we would end up getting over here in terms of the amount of helium is actually 99.3 grams. Huh, that doesn't make sense. Looks like we've lost something. Especially if we take a look at the periodic table and we look at, like, for instance, how many protons hydrogen has. Hydrogen has 1 proton. That's our first one. It has an atomic number of 1, has 1 proton. So we have a total of 4 protons coming together. But helium has 2 protons. There's things missing. What happened? So what happened is there was mass loss that got converted to energy. And I'm actually going to write this as important notes. Asterisk. There was mass that was lost. And it gets converted. Is my pen running out? Converted. Let's see if I can find another blue one. Oh. That's better. The mass loss gets converted to energy. We talked about how if I show capital E, anytime you see capital E in science, that's referring to energy. So up here, we can add plus energy. So we're losing some mass in this process, went from 100 to 99.3. Energy is coming off of that. Now, you guys may be familiar with this equation. It's a pretty famous equation. E equals mc squared. This is Einstein's equation. So you may have seen it, but maybe you don't quite, you don't know what this means. Now, this has some huge implications into kind of how much energy is actually coming out of this. I just told you that capital E, whenever we see that in science, is referring to energy. And for funsies, I'm going to do this in red to make it stand out. So E is energy. M, we've seen M in our in other equations like the Newton's law of universal gravitation. We had M1 and M2. Mass. The only thing that maybe you're unaware of is C. C is actually the speed of light. Speed of light. Now, what this tells us is this is basically a way to quantify this change in mass, change in M from 100 to 99.3, how much energy that actually creates. Now, this doesn't look like a whole lot of mass. This is only 0.7 grams. To give you an idea, like if you have a sugar packets are like, I don't know, 2 grams of sugar. So this is less than that. Now, this is hypothetically speaking, but even if we have a small amount of mass that is lost, because we're multiplying it, not just by the speed of light, which by the way is a very, very big number, but it's the speed of light squared. So it's a super big number times itself that ends up equating to a huge amount of energy. That's the energy that is pushing outwards, that is basically holding a star up against the crushing force of gravity. And this is a ton of energy. Just to kind of put it in perspective, I'm going to put in parentheses underneath here, that if you had 1 gram of hydrogen fusing into helium, just 1 gram, that's enough to power a whole city like San Francisco for months. For months. And the sun doesn't just do 1 gram every once in a while. The sun does 600 million tons per second. $600 million per second. So now you can get a sense of how much energy the sun is actually producing. Small amount of mass lost, we call that a mass defect. Small amount of mass that's getting lost, but so much energy that's being made from that. Now, again, I want to mention that this is happening in the sun right now as we speak. That's what characterizes the main sequence. Our star, the sun, is in its main sequence right now, and it's going through its hydrogen, turning it into helium, and that energy is coming to us, which is super nice. Now, a couple of things before we move on from this, I want to add that we oftentimes refer to hydrogen in the star as its fuel. So I'm just going to write fuel up here and point at hydrogen. Hydrogen is the fuel. Think of it as fuel for the star, and it's burning that fuel just like you burn gasoline, and it's converting it to helium, and we're getting energy from that. And don't forget, this is also happening during the main sequence. During main sequence. Okay. You can see I'm getting towards the right-hand corner of my page, just to give you some perspective. If you're finding you're all the way to the end, you can kind of go onto the backside, or you can snake your way down. We're going to snake our way down anyway, down the right side. As long as your arrows are following in that direction, that's fine. Okay, so if we're saying that hydrogen is the fuel for the star, then just like in your car, if you're using your fuel, you could run out of fuel. So what happens when the sun runs out of fuel? That's going to be our next arrow. So I'm actually, I'm bored of the simple arrows. I'm going to draw a cool, like kind of 3D or a block arrow. There's my block arrow. I'm kind of going down this way. So we're going to talk about what happens when it runs out of hydrogen fuel, H fuel in the core. So what happens when it runs out of hydrogen fuel in the core? This is when we can say the star is starting to die. Starts dying. So the main sequence, it's just living its life. Now it's running out of hydrogen fuel in the core. It's starting to die. I want to redraw the our kind of donut shape, our main sequence donut shape. We're going to draw it over here, but some things are going to be different about it. Now, remember that it's hydrogen fusing into helium, hydrogen fusion in the core, that's causing that thermal pressure pushing outwards. But if we've run out of all that fuel, we're no longer creating that energy. And now there's no longer arrows pushing outwards. We still have the gravity arrows pushing inwards because this is still has a lot of mass. But now there's no longer arrows pushing outwards to balance it out. Remember that hydrostatic equilibrium is that nice balance of outward arrows and inward arrows. Now we only have gravity. We don't have the outward force of thermal pressure from fusion. It's all just inward arrows. So what happens is we get what's called a core collapse. Basically, the star starts collapsing in on itself. Core collapse. Now we talked about if this thing, I want you to imagine this thing is kind of contracting in, it's squeezing in on itself under the force of gravity. We already saw what happens if things come together. If we go all the way back to the beginning, dust and gas gets contracted from gravity, further contraction. We see the temperature goes up, the temperature goes up. Guess what? The temperature is going to go up when this happens. Collapses in, all those molecules and atoms and stuff are going to start hitting each other. Temperature goes up. Let's put that in parentheses. Temperature increases. And as the temperature increases, that's enough energy to actually cause fusion to start again. So we had fusion happening over here, required energy, required enough gravity to kind of cause fusion to start. It's gonna happen again. But this time, instead of hydrogen, we basically ran out of hydrogen. Now we're gonna start fusing helium. So the core collapse causes the temperature to rise enough for helium fusion. So now basically what we were making in the previous step is now the fuel for our next stage. Helium's going to be fusing. Now, if we're going to do another kind of like zoom in, this is going to be a super simple, like this is what happens at the atomic level when we have fusion of helium. If we have 3 heliums, those can come together to make carbon. And again, this is overly simplified, but we're going helium. If we put 3 of those together, we end up getting carbon. There are some intermediate steps, like we end up getting like beryllium before that. But just to simplify it, this is the next like main element that ends up being made in the star. And guess what? We're made of carbon. So, and all living things are made of carbon. This is where the carbon comes from that you are made of, which is nice. So this ends up fusing. And remember, fusion actually creates lots of energy. I'm not drawing it over here, but we're creating a lot of energy. There's still a mass that's being lost. Remember, mass is being lost. We're going to see that happening again. And here's what the star ends up looking like. We're going to make this a little bit bigger. I'm going to zoom out so we can kind of compare it to what my collapsing star looks like over here. I'm actually going to draw this in red. And I'm going to draw the core in the middle. You're like, wow, that's pretty big. Why is it so big? Now, here's the thing is that we have this fusion of helium into carbon, produces a lot of energy. So now we have those outward arrows again that helps to counteract the force of the inward pull of gravity. Now, here's the thing is we're looking at this thing and it's like, wow, that's really big. We actually call this a red giant, which I'll label in a second. But this star actually weighs less than what we started with. Remember, this thing is constantly losing mass. And so you're like, why is this so big then? It's the volume is bigger. So it's like blowing up a balloon, but it's not actually increasing in mass. In fact, like we said, it's constantly losing mass. So one of the reasons why it blows up so big is because our gravity arrows are actually smaller. If it's less mass, that means gravity is less. So the smaller arrows pushing in means that the thermal pressure pushing out can counteract that a little bit more. And so it spreads out, it expands. So we have smaller gravity arrows because the mass is less. And so that makes it get bigger. And actually to the right of, or sorry, left of that, just kind of over here, I want to indicate that because that's super important, is that it's the volume that increases. So how much space it takes up, volume increases. But mass is still decreasing. Volume increases, but mass is still decreasing. So again, mass is decreasing, smaller arrows, smaller gravity arrows, because that mass is less. And so these arrows can overpower that, and that's what makes the volume larger. So I want to add a little bit of information down here. Increased thermal pressure from helium fusion into heavier elements is what's happening here. Heavier elements. Specifically, we're looking at, we mentioned carbon. We're also going to see oxygen popping up. We know how important carbon and oxygen are. But this stage, if you were to name this, if someone came up and said, what are you going to call this thing? You're like, hey, it's red and it's giant. So there are stars in the night sky right now that are at this stage, in the red giant stage. They've basically run through their hydrogen fuel. Now they're burning helium, and they're big red stars. Betelgeuse is a red giant or red supergiant. That one's probably going to go supernova pretty soon. Now, at this point, we actually have two different paths that we can go depending on how massive the star was originally. So if we're saying maybe this star was originally like an average mass star, like our sun is an average mass star. It's not super, super big. It's probably actually a little bit more on the smaller side compared to some of the stars that are out there. But let's just kind of go, what's going to happen to an average mass star? And I'm going to go to the left and we're going to go this way. So I'm going to zoom out so you can kind of see where we're at. We start over here. We went all the way to the right. We're snaking down, and now I'm going to go back this way to the left. So we're going to draw an arrow going this way. And I'm going to say for an average mass star on this arrow, average mass star, like our sun, like the sun. It's not large enough at this point to fuse heavier elements. So average mass star, like our sun, is not large enough to fuse heavier elements. Because basically, I want to remind you that at this step, we have helium fusing into heavier elements. But what happens when helium runs out? Just like we saw before, we're going to get another core collapse. So this is going to collapse inwards. That temperature is going to increase again, but that's not going to be enough energy if it's not massive enough in the first place to actually cause the reaction, the nuclear fusion reaction, to happen again. So it just collapses one more time. And when that collapses, it makes the inside really, really hot again, not hot enough to cause fusion of heavier elements. And we get this rebound. And that pushes all the stuff on the outside kind of outwards. And we get something that looks really, really cool. So over here, I'm going to draw what that looks like. What we have is kind of the dead core in the middle. So here's the core of our star. And then around it is all the gas and dust that gets rebounded. It's super, super hot. And that has all the elements that were being made. Dust and gas. And you may notice there's some similarities to this cloud, to what we started with. it's a beautiful thing that oftentimes what we see here is that dust and gas can later come together under the force of gravity, and it may start making new stars. It's like a circle of life. So what we have right in the middle, this dead core, is called a white dwarf. White dwarf. And this around it is called a planetary nebula. Planetary nebula. So white dwarf, I'm going to draw an arrow from white dwarf going to this, and then planetary nebula is the cloud of dust and stuff that's coming from it. Now, again, I want to remind you what happened here was we had helium fusing into carbon that was pushing outwards. Helium runs out, this collapses. It gets hot, but not hot enough to start fusion again. That collapse makes the core really hot, and then the other stuff rebounds and pushes out, and that's what all this dust and gas looks like. Now, this thing is super hot and typically looks very white because of how much energy is coming off of it, but this is no longer a star. So underneath here, in print or a little asterisk, no longer a star. And why? The thing that makes a star is if there's nuclear fusion happening in the core. So it's no longer a star because no more fusion. Now, as time goes on, this nebula will spread out and disperse. And what's in here, this dead core, here's our white dwarf. Eventually, it'll cool off to the point where we will no longer be able to see it. It'll no longer glow. It's lost its energy. We call this a black dwarf. These are one of those things where we won't be able to see it via the visible light spectrum, but we might be able to see some low energy waves coming off of cooling kind of these dead cores of stars. So this is what's going to happen to our star, the sun, is it's going to go through this path that we drew right now. It's here. This is happening in its core. When it starts dying, hydrogen runs out, it collapses, it'll initiate fusion of helium. By the way, at this time, this will spread out far enough to engulf all the inner planets, probably Earth as well. If humanity is still around, we won't last very long with that. And then as that happens, this is the dead core. The nebula spreads out, and it'll go this way. But what happens if we've got something really, really massive? So something much bigger than our star. So if we're saying this is kind of the average star, average mass star, what if something so big and so massive it's going to have tons of gravity? We're going to go back to this stage right here and kind of go down. You can see how much space I got at the bottom. We're going to do another arrow going this way, and I'm going to go to the left like this. So I'm going to do an arrow downwards from here. And I'm going to specify if it's a really large star, so super massive. For large stars, we're talking like 25 times the mass of the sun. This is enough mass. The mass is going to be large enough that another core collapse will initiate fusion again. Of even heavier elements. And this will go all the way up to iron. The symbol for iron is Fe. So again, what's happening is at this point, we had helium as the new fuel source, and that is being converted into carbon, maybe some oxygen as well. When that runs out, this collapses, but if there's enough mass there, it'll heat up enough to go and start fusing carbon and oxygen into even heavier elements. And what happens is a series of collapses and reigniting and collapse and reigniting. And actually, it looks really cool what the core ends up looking like. So I'm going to draw an arrow going to the left here. I want to draw what the core looks like after successive collapses. We actually get what kind of looks like an onion. In the middle, Fe is iron. So this is the last thing that a star can fuse. I'm just going to draw the rings first. There's a number of rings we're drawing for this. Let's see. 1, 2, 3, 4, 5, 6, 4, 5, 6. Smearing this. Gross. So we get these series of elements, oxygen, carbon, helium, hydrogen. So basically what I've drawn is the core of a dying star. And if the core ends up looking like this, it's not a small star. This is a supergiant. Core of dying supergiant. Now, the reason why it ends up looking like this is because remember, hydrogen was the first fuel source. It was being fused into helium. So hydrogen into helium. When hydrogen ran out, we got a collapse. It got hot enough to reignite, and now helium was the fuel source. It was being converted into carbon. Helium probably ran out, got another collapse, and then it ignited carbon. Carbon was making oxygen. That collapsed when it ran out of carbon. Then oxygen started fusing. We got all these other elements, silicon, and then finally, eventually, it started fusing iron. And what ends up happening is the remnants, the last little bits of some of these lighter elements, because they're less dense, they get kind of pushed outwards with the heavier stuff forming in the middle. So iron is the heaviest out of all of these. It's going to sink towards the middle of this, and it kind of looks like an onion. Now, one thing I want to mention is there's so much energy because there's so much gravity and mass pushing inwards on this that it's really, really hot. And there's a reason why I'm using blue for this. So this is hot enough to turn blue. We call these blue supergiants. So some of the hottest, brightest stars in the sky are blue supergiants. I mean, sometimes they're hot enough to be blue in their main sequence, but at this point, tons of energy. Now, if it's at this point, we're at the, and again, this is after successive like collapse, and then it blows up, and then it collapses again, and it blows up, and every time it goes faster and faster. By the time we're forming iron, it's going to last for maybe a couple more days. And that's super short in terms of like universe time. Couple of days, we get one final collapse when we're basically run out of our last bit of fuel. So I'm going to draw an arrow to the left for one final collapse. One final collapse. Now, this is going to collapse with so much force and energy that it basically it's just going to blow up. Massive explosion. We call it a supernova. supernova. And this is such an energetic explosion that all other elements on the periodic table, again, so far we've got hydrogen, helium, we got these other ones, carbon, oxygen. Iron is the last one that can be made in a dying star. But once the star collapses one final time, that energetic explosion will create all of these other elements. All these other elements come from supernova. All other elements created from immense heat and energy. Little quick quiz question for you guys. I'm telling you, this is one of the most energetic things in the universe. If we wanted to look at kind of detect supernova with a telescope, we probably want ones that can detect higher energy wavelengths. So we're looking at X-ray and gamma ray for that. Okay, so we're not done yet. I've got a little bit of space to the left. Let's see, I've got a little bit of space. We can try and fit this in here. Let's say we got something that is big. So again, we're looking at like super large stars going in this direction. But at this point, we can have slightly different fates depending on the original mass of the star. I'm going to draw an arrow kind of going upwards this way. And let's say it's 20 times the mass of the sun. 20 times mass of sun. What we end up getting is something called a neutron star. Neutron star. Now, this thing is super, super dense. It's basically pure neutrons. Pure neutrons. Now, we can kind of get a sense of why it's so dense. Let's see. We know that normally atoms look like this. So you don't have to draw this or anything. I'm just showing you for educational purposes. Remember that in the nucleus of an atom, we got protons, we got neutrons, and then the electrons are whizzing around the outside like that. Atoms are mostly empty space. And the neighboring atom, if you have matter, what things are made out of, that next atom is going to be maybe like this. It might be sharing some of these. But look how much empty space is in here. A neutron star is just a bunch of neutrons stuck together. It's so dense because of that, just to put it into some context, so dense that if you had just 1 teaspoon, that would weigh 5.5 billion tons. Can you imagine that? Can you imagine anything that if you just had 1 teaspoon of it, it would weigh 5.5 billion tons? It's hard for us to wrap our head around that. So that's a neutron star. That is the fate. After a supernova, we can get neutron stars. Now, it's called a neutron star, but there's no fusion happening in the core. So this is not technically a star, even though it's called a neutron star. But let's just remind ourselves there's no fusion happening here. No more fusion. Now, we do have the possibility of having even more massive stars than that. There are some stars that are 30 to 40 times the mass of the sun. And what happens after a supernova is different for them. So I got just this bottom corner here. We're almost done. We're talking 30 to 40 times the mass of the sun. 30 to 40 times the mass of the sun. That's where you get a black hole. And this is actually like we talked about a little bit in terms of gravity, how it works. It's actually a distortion of space-time. So things that have mass will actually bend the fabric of space-time, and things like to fall towards other things that have mass. A black hole is literally, it's undefined. It's like if you were to actually like have a hole in the fabric of, I mean, that's why it's called a black hole. But there's so much light and energy, sorry, so much gravity. I'm just going to write down here, so much gravity, capital G for gravity, that light can't escape. So that's only for the largest stars, turns into a black hole. Now, we basically have a whole flow chart now that has what happens from star birth to what happens to a star during its main sequence, and how fusion happens, what happens when it starts running out of fuel, it starts dying, and the successive collapse and reigniting, and then collapse and reigniting, what it looks like for an average mass star in terms of its death, and then the super large stuff. One last thing I'd like you to add, if you got some room on the front, I've got a little bit of room up here. Just a note that sometimes is a misconception for students. More massive stars have a shorter lifespan. And the reason why is because it burns through its fuel quicker. Again, it's good to think of like hydrogen in the star as the fuel. And so if you've got something that is really, really massive, that means there's more gravity pushing inwards. That means it's going to push more of this together in a shorter period of time. It'd kind of be like if you're comparing a supercar, like a Bugatti, something or other, some really, really fast car compared to like a Honda Civic. The super, super fast car, like the Bugatti, I think the Bugatti Veyron, I don't know what the newest Bugatti is like, but I remember reading that you could have, if you put the foot on the gas pedal all the way down with a full tank of gas, you would run out of gas in 10 minutes. Whereas if you did the same thing with like a Honda Civic, you get further than that. Obviously, it'd be more than 10 minutes, but basically the larger the star, it's burning through that fuel quicker because more gravity is going to push inwards, going to force that hydrogen fuel to come together quicker. Okay, that looks good. Thank you guys for listening. I appreciate it.